video, so it's a little hard to know when I'm really in the air. So I'll just twiddle my thumbs for a moment, but I'm confident that the stream is really going. I think it is now. So this is live coding again. Today the topic is sealed tables, a new experimental optimization feature for raptorjit. We did a stream yesterday that was a really raw brain dump, all blah 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 about what the the context of the whole idea is. Very rough, very raw. And what we're going to do today is a bit of coding instead. So instead of talking a lot, I'll talk a little bit at the beginning and see if we can actually write some code and look at some interesting things. So let's dive straight in. I'm keeping a little GitHub project to keep track of what we're doing. I had said yesterday that the next step was to define the problem that this solves and why it's the right solution. But it's way too early for that, actually. I'm going to chuck that back over here, and we're going to do an experiment instead. Hack an experiment to learn something. That's where we're at now. That's what we're doing. And I whipped up already, I did a little bit of preliminary hacking. I'll tell you what that is. So hopping over to where we have some code. So I'm going to very briefly remind us what the feature is all about. So the idea is that in Lua we have a lot of tables. We might say t is a table with x is a function. We might write something like this. So then we have a global variable t, which is a table, hash table, which has one entry, which is called x and is a function of two arguments that adds them together. And then in our program, we might say something like t.x 41, 1, and we expect to get out 42. And the question is, how is that calculated? So normally this would be a hash table lookup on a global variable t, and that returns a hash table, and we do a hash table lookup to get the key x from that. Then we add these, we get a function out of that, we call it with these parameters, and we get our result. So it's a lot. I mean, two hash table lookups. It's quite a bit of work just to call a really trivial function, and that's not necessarily so nice. It would be nice to have some shortcuts. And there's an optimization called loop optimization in LuaJIT that is also in raptorjit by inheritance. And this is a great optimization that takes away all the hash tables, but the problem is that it's not universally applicable. So loop optimization is sometimes there and sometimes not, and if you depend on it too much, then that's a recipe for trouble, because it's not always there. When it's not there, things will be nasty. So in the worst case, you do a lot of testing in simple kind of workloads where loop optimization is very effective, and then in the real world, you manage to find cases where it doesn't work. So the idea with sealed tables is we will be able to say something like seal the table T and seal the global table, and then the compiler would take more liberties. We've promised the compiler that these tables are changing very infrequently. So for example, that we're prepared for changes to those tables to flush and regenerate all machine code in the system. So it would only be done when we're patching things or whatever. And then the compiler could take more liberties, whether with or without loop optimization. It could just inline a lot more stuff. So we're gonna go straight over to an example now. But this is what we want to do. This is where we want to get to. We're only going to take a small baby step today. We want to get to having this seal primitive that says that a certain table can be very aggressively optimized for reads at the expense of writes. So I whipped up a little example program called seal1.lua, which is going to compile kind of in a bit of a disappointing way with if we use the normal implementation, pardon the background noise, use the normal implementation, and we turn off the loop optimization because we want to think about the case where that doesn't apply. So we construct a table with a key called x, which is 10,000, and a key called y, which is 10. Then we're going to do a loop that calls or that accesses this table. It's going to accumulate things in an accumulator variable, which is a local. So a little loop is going to update the accumulator to be the loop index plus the square root of t.x, which, I mean, we can see that t.x is 10,000, so we know that this is 100, but the compiler doesn't necessarily, and then it's going to multiply that square root by the square of t.y, and again we can see that y is 10, so when we square that we're going to get 100, so we can see that this is going to be loop index plus 100 times 100. But the compiler doesn't necessarily see that. So let's now look at, we're going to do this hacking actually on LuaJIT rather than raptorjit, because I'm replacing a lot of the diagnostic tooling in raptorjit, and I've really focused on the case where you have a large application with a lot of profiler data and a lot of machine code generated and that kind of thing. And that I've got working really well. But in the case where we're iteratively hacking on the compiler for a really tiny example, and what we're expecting is that most of the time we're just going to crash because we're kind of poking around in code that we don't understand very well yet. It's actually going to be easier to hack that directly on LuaJIT. So we'll do this on the LuaJIT 2.1 branch, and then when we have something, we'll port it over to the raptorjit branch. So let us run this with LuaJIT 2.1 and with loop optimization disabled and see what code we get. Maybe we'll try to keep everything on the screen at once. So I saved a pristine LuaJIT 2.1 binary, and we're going to disable the loop optimization, and we're going to dump the intermediate representation code, and we're going to run that on seal1.lua. And this is what we get. Okay. What just happened is we ran this program. We asked the JIT compiler in LuaJIT to dump the intermediate representation of any code that it generates, and that's what we got. So the code that we see here is what this little loop compiled into. So let's just take a look at this. I mean, it's quite a bit of code, right? We have 31 IR instructions. Each IR instruction is probably, on average, something like 2 machine code instructions, 2 or 3. So it's a fair bit of code for each iteration of the loop. And why is that? Well, if we look at it, just a little bit of the things that we do here, we load the globals table first, because we're going to access some globals here. Math is a global, T is a global, so we're going to need to access the global table. That happens here. Then we go in and we check that the globals table is the way that we expect. So when this code was compiled, the globals table was a 64 bucket hash table, and so what we have here is we pull out the mask, the hash table mask. So this is what we mask the hash code with to make it into an index into the hash table, and we say that should be 63. The mask should be 63 because we have 64 slots in the hash table. So this is a precaution the compiler is taking in case the globals table has grown since this machine code was generated. If that had happened, then this guard that we see here, guarded assertion, which we recognize by the greater than sign there, it would fail, and this machine code from this point would bail out, and we would JIT some new code. So this is something that sealed tables potentially helps with. So this machine code here is very defensive. It's taking care of the case where the significant changes might have been made to the globals table, not just changing values, but actually growing the hash table. So it's a lot of stuff that it needs to defend against. And going from there, we then load the value. Well, once it's confirmed that the globals table is the shape that we think it is, then we can calculate where to find the math field. So this is where we're loading the global math table. And then from that, we need to do basically the same thing. We need to make sure the math table still looks the same as it did when the machine code was generated. It was a 32 entry table. And once we've confirmed that, then we can load the square root, which is going to give us a function. And then we're also going to load our t global. We don't have to check the globals table again now because it's the same table, and we already checked its shape when we pulled math. So pulling t is a little bit more streamlined, but then we still need to check that the t table looks like we think now. It's a 2-entry hash table. We can see because the mask is 1. It's a 1 bit. It's using 1 bit of the hash code of the keys to find the slots. And in there we look up x and y. So okay, so all of that work, which is like 20 IR instructions. Let's assume it's something like 50 machine code instructions, something like. That's just to do the lookup on these fields to say we need to find a global called math, and then after we found that, we need to find a field called square root, and we need to find a global called t, and within that we need to find a key called x and a key called y. So a lot of stuff, right? So this is a tremendous amount of work being done, and it will be nifty not to do it. Okay, and then once that's done, we're actually performing a floating point square root operation. Your Lua numbers are floating point numbers, so we actually do square root, and we actually do some multiplications. So we actually perform all of the arithmetic. So anyway, I guess that this is kind of the way you would expect it to look if you just think about the semantics of the language, right? So every access to a global is a hash table lookup. Every access to a function is also a hash table lookup. And if you want to do any arithmetic, then you need to do some calculations. Fine, but this we want to use this sealed tables idea to optimize the hell out of this is the idea. So just to give the idea, if we knew that the globals table was sealed, so in other words, that we knew that since the machine code was generated, no changes had been made to the globals table, then we don't need to do this kind of stuff here, checking its shape, because the globals table is invariant. So we just don't need to check it anymore if we would have that sealing. And similarly, if we would seal the math table, then we could just look up the square root function at when we're recording the machine code, and then we already know, we already have the reference to that function. We don't need to look it up at runtime. And similarly with with all of these hash table lookups, if the tables were sealed, if we were able to treat the kind of hash table lookups as compile time constants, then a lot of stuff would disappear. Anyway, I'm talking too much. I did a really quick hack yesterday to just go into the code where table lookups are recorded and just make everything kind of sealed. So this is pretty extreme thing to do. I'm sure it would break real programs, but it should be interesting for looking at on this small example. So first I'll just run this new version I have. Make sure we're on the right commit. Yes, okay. Here is the crazy kamikaze hack version of that. If we run with current checkout. So that's different, right? Let's hold on. Let's do a side-by-side comparison. Close to side-by-side. So on the this is a demonstration of what we want to be able to, the kind of things we want to be able to do with sealed tables in some kind of a disciplined way, but we'll get to that. So before we had all of this stuff for hash table lookups, and then we had all of this arithmetic being done. So basically all of that code has been replaced by this one instruction here, which just inlines the constant 10,000. So that is what's happened is, just pull up the source again for reference. So here we did, well, here we looked at t.x, and on the sealed version, the compiler, when it was generating this code, it looked up t.x, it found that it was 10,000. It decided to treat this table t as sealed, so it says this is not just 10,000 now, this is 10,000 always. The result of this table lookup is always 10,000. So it just basically rewrote that to be the constant 10,000. Then it wanted to take the square root of that, so the existing constant folding optimization in the compiler already takes care of this. When the compiler sees a square root operation and the argument has been replaced by a constant, it just it takes away the square root and makes that a constant. So that will turn into 100. And then a similar thing happens over here. T.y, we do a lookup on that, and we get 10. We convert that into a constant. We square it. We get 100. And then, so what we end up here with is I plus 100 times 100. 100 times 100, that's also something that goes into the constant folding optimization in the compiler, and that's where we get this magic constant 10,000. So that 10,000 represents a square root, a square, a multiplication, lookup of the global math table, a lookup of the square root function in the global math table, a lookup of the global t table, a lookup of x and y in the t table. So a lot of work. Maybe something like 50 machine instructions has now been collapsed into much less, more like one machine instruction to add a constant to a register. So this is what I want to be able to do when I'm writing programs, and I have something like an important module like the math module that I'm in practice. I'm not very often going around and redefining math.square root, and if I'm quite willing to flush the machine code if I need to do that. If I really need to redefine math.square root, for example, I'm quite happy to have the JIT run again and generate new code for that. So this looks very promising to me. The only problem is that this implementation I've done is just like totally wild hack. So what we're going to do now, well, I mean, this is the demo at the start. It's going to be a hard slog from here going in, right? Because now we need to actually try and understand the code a bit better and try and figure out how to do this in a reasonable way. So yeah, that's what we're doing. So this was the fun part. Now starts the real work, depending on what you think is fun. So let's take a 5-minute break and then dive into the code. Look at what my kind of nasty hack looks like, and start reformulating that. Have a bit of a look at the way table lookups are recorded, and think about what is the right way to do this, and think about how to handle other special cases like tables that have metatables, all that kind of stuff, tables that are arrays. Let's come back to that really soon. Okay, back we come. So what we're doing now, it's getting bright outside as the sun comes out. What we're doing now is we're going to do a little bit of hacking. So let's just dive straight in and look at the code where table lookups are done. Oops. Hop over into a fresh Emacs, luxurious, and we're doing this on the LuaJIT source tree actually. We're going to go into a file called ljrecord.c. So this is the trace recorder. So the way that the compiler works is by tracing code. So when it runs a lot of code interpreted, and then when a certain position in the code gets hot, it says, well, we want to compile this, we want to JIT compile this. So and then what it does is it interprets it one more time, but while it interprets, it also as a side effect it records what actions were taken, and then it generates machine code corresponding with that. And that all happens in this file here, ljrecord. So what we want to do is we want to go and find the bytecodes for table lookups and see how those are recorded. Let's hop over to the reference documentation as well. It's really nice documentation actually in the LuaJIT world for the bytecode and intermediate representations. They've done a great job. And raptorjit is a fork of LuaJIT, so we inherit all of that. It hasn't diverged in any interesting way in this part of the code base at this stage, so everything here is relevant. So there's a bunch of bytecodes like gget, tgetv, tgetS to do table lookups in various ways, depending on whether the key is a variable or a string or literal, this kind of thing. So what we want to do is see how those are recorded, and then see how we can apply this sealed tables optimization there. So we're just going to search for getv, for example. Okay, so here we are in a great big switch statement that's checking which bytecode is executing and then recording some appropriate machine code to track it. So what do we have here? Table operations, a global get and set here, tgetb, tsetb, variants handled there. So a few different variants, and in every case it compiles down to a call to this ljrecord an index lookup. So that's the function that does the work of recording how a table lookup should be compiled. So that seems to be where we need to be poking. So let's hop in there. Record index load store. So how much code are we looking at here? It's quite a big function, which is a bit fundamental because the semantics of table lookups in Lua and in LuaJIT and in raptorjit is pretty interesting. The fundamental data structure in Lua is the table, and there's a few things about a table. A table can be a hash table. You can put more or less arbitrary objects as keys and get out values, and they'll be hashed. It can also be an array. So if your keys happen to be 1, 2, 3, 4, 5, 6, 7, and so on, then that's actually special cased in the runtime system. It will allocate, instead of a hash table, it will allocate, or in addition to the hash table part, it will allocate an array you can just index straight into, which is faster and more compact. If what you're doing is fundamentally array lookups by index, and you can also have something called a meta table, which is really interesting. So in a meta table, you say when you want to do a lookup on this table, or an insertion, when you want to do an operation on this table, you should figure out how to do it indirectly by consulting this other thing, and that can be a function, for example. So you can have a table where every time you try to look something up, it actually calls a function to calculate what should be there, and similarly, when you try to set a value, it calls a function to implement that. So you can do weird and wonderful things in this way, and you can also kind of have you can also use meta tables a bit like prototypes in JavaScript and so on, where you say I've got this got this table here, and if you ever look up on something you don't know that's not present in that table, then you should defer the lookup to this other table somewhere else. You can do kind of prototype-based or object-oriented programming in that way, which is actually really popular in the Lua universe. So the thing is that table lookup is a big topic in general. There's a lot of different kinds of tables. The semantics for table lookups is quite involved. So we're gonna just pick something to start with, because the point here is still to mostly as a learning exercise. So what we're gonna say is we're going to go for something simple, powerful, in like a little bit in the spirit of Lisp, I would say. Lisp has a history of putting in these kind of fairly extreme features like fexpers and macros and stuff, which give a lot of power to the programmer, possibly more power than they really should have. But it's if you you don't really understand what you're doing yet, you kind of err on the side of trusting the programmer rather than the compiler. So we'll do this in the most kind of dangerous, nuclear, powerful way that we can at the moment, which also will be the simplest to implement, I hope. So, and what that's going to mean specifically is that what I want to do is that when we do a lookup on a table, if that table is marked as sealed, then however the lookup was performed, whether it was a hash lookup or whether it was an array lookup or whether it was some kind of more complex metatable kind of lookup, what I want to do is take the result, inline that into the machine code as a constant, and just emit the absolute minimum of kind of tests and guards to make this safe. So what I would imagine is that when you do a lookup, we'll when we record, we'll do the lookup for real. We'll actually go into the hash table and see what the value is. Then we'll put that value directly into the machine code, and it will be protected by two guarded assertions. The first is that the same that it's the same table. So the machine code we generate is going to be specialized for one specific table, like the global table or the global math table, or something like that. And the machine code is going to check that it's still the same table that it's dealing with, so that so it's not too eager. It doesn't kind of take a value from one sealed table and then use that for other sealed tables or unsealed tables or whatever. And we'll also assert on the value of the key that we're looking up in the table. So what this means is that if your code is always looking in the same table with the same key, then it's just going to compile once, and it'll only be a formality to do these checks. And particularly with checking the key is the same, if the key is a constant, that check should actually just disappear in optimization. But if you're doing something more complex, if you have compiling a loop where you actually look in a few different tables, maybe they're all sealed, or maybe some of them are sealed and some of them are not, and you're using a few different keys for your lookup, maybe you're using array indexes or something like that. The way this implementation would work is that for every combination of a key and a sealed table, it would generate specialized machine code. So if you have a lot of different combinations, you'll end up with quite a lot of machine code and quite a lot of branching between, which is probably not what you want, but this is going to be a dangerous feature intended for programmers who are going to think about, understand and think about how the code is going to compile. And in the very worst, even if it all turns out to be completely impractical, I think we're going to learn quite a bit about the way the compiler works, the way it compiles table lookups and that kind of thing. So this, I don't think that we can lose in this. This seems like a great use of our time. So let us. I'll just tell you what I've figured out so far, just briefly looking at this function yesterday. So first of all, this record indexing, this is actually recursive. And that's to deal with metatables. So here we are doing this fundamental operation, record and indexed load or store. And it can be that we need to do a metatable lookup here, because it could be that it could be a table with a metatable. It could also be some FFI object like a C pointer that has a metatable attached to it. So there's a lot of different ways that this can be implemented, and some of those require a recursive call to this. So we would go out to record a meta method lookup, and from there we would end up coming back in, if I recall correctly. The meta method would go off, do a lookup, yeah, and then it would come down and continue recording. So a lot of stuff can happen, and in line with what I was saying before, what I want to do is that if it does turn into a really complicated long chain of recursive meta methods and all the rest of it, I just want to capture the final outcome of that, and we'll see if this is fatally flawed in some way. But it can go off and do whatever it wants in order to get the value, and then we're just going to take that value, stick it in the machine code, and just guard that the put in guards to say that this machine code is specialized for this particular table and this particular value. So the assumption is going to be that you would always get the same value every time you do a lookup. And in this sense, sorry, I said I wouldn't do so much blah blah, but I'm going to do a little bit. In this sense, the sealed table is a lot like memoization, but on steroids. So the idea with the memoization is that you have a function, and maybe it takes a long time to run, and it always returns the same result for the same arguments. So you put a cache in front of it. You had a function, and now you make it a table. So if your function is the factorial, and you want the factorial of 10,000, then it takes a long time to compute. But if you memorize it, it'll only compute that once, and then it'll remember the result, which is nice as a speed up. And as a programmer, you just need to deal with the fact that if there are any side effects or anything happening in the computation, then they will only happen once. So it's something that needs to be used with care. And it's basically the same thing here, right? I would say that this sealed tables is like memoization, except that the result is not just cached in a hash table. It goes a step further, and the result is actually inlined as a constant into the compiled code. And this is possible because our JIT compiler is generating code so late. So at the time that we're generating code, we actually have computed the value. So most compilers, the code generation happened a long time before you ever would see what the actual value would be. So this you couldn't do anything like this in GCC, for example. It's just the compilation happened too long ago. You don't have visibility of any of the relevant information, but we can do it here, and we're going to do it. I'm going to see what happens. So what that means is we need to somehow deal with the fact that this is all very recursive and just do our optimization on the last step. So if we have a chain of 10 different chains through metatables and everything, we just want to let that happen as it normally does, and then at the very end we want to just capture the value. And while I was browsing this code, I saw a really nifty little trick, which is rollbacks in the intermediate code. So there is this cool function to do an IR rollback. So what that means is, if we just look briefly again at our generated code. So this IR code that we see here, this is being generated basically sequentially. So as the recording process goes along, it keeps appending IR instructions, and as it appends them, it actually does kind of backwards looking on the fly optimizations to combine things, constant folding, that kind of thing. But putting that to one side, basically we're generating this step by step linearly. So the implementation strategy that I have in mind, and that I did in my quick hack, is that if we look at this so-called slow version of the code that does a lot of lookups, my thinking is that we actually generate all of this code, we do all of this, we do all of these lookups in the normal way, but before we finalize this, before we say we're ready, at the very end, we do a rollback. So we rewind the IR code to actually take away all of those lookups, and then we just insert the value as a constant. So that's the big idea here, that we can implement the sealed tables thing just as a little additional step at the end of table lookup that doesn't really have to get too much into the gears and all the complications with metatables and everything. We just let that all happen as it would, and even generate the code that would be needed. But then we just say, okay, and all that code, by the way, we don't need that. Where you're going to replace it with this constant. So to do that, I'm just going to start programming this, and where needed, I can hop back to the code, to the quick hack code, which I have up. I have up the diff of my quick hack over here. So if I get stuck on something, I can hop back over there and see. But so we wanted to be looking in record an indexed load store. So because because we want to I'll be doing that in this Emacs is where we're working. Pardon me. So I was saying the implementation strategy relies on being able to generate all of our code for a lookup and then to roll that back and replace it. So the first thing that we're going to do in here, and I'm not going to think about the recursive case for now. I need to come back to that. So I mean, I'm doing this, I'm just pretending that this is not used recursively, that there's just a single call, and this will probably break things, and we'll probably get a segfault or something, but we'll take that as the second step. For now, we're just going to remember the IR reference where we started. We're going to call this rollback start point. This is just to match the naming here. There's a rollback reference, which I'm not sure what that rollback is used for, but it's some smaller thing. This is going to be rollback all the way to the start, and we're going to initialize that to the latest IR instruction. So an IR reference is basically a number. I mean, these are IR references here, right? So if the IR reference when we start doing the recording is 3, we're going to remember 3, and I'm going to generate all this, and we're going to do a rollback to 3, which will then drop, all of those instructions. That's what we're doing here. And the way that we reference that is we say the current trace that we're compiling, the number of instructions that it has. So the number of instructions it has corresponds with the current latest IR reference. So if we were compiling and we were up to here, then the number of instructions would be 2. 2 would also be the number of the latest, the reference to the latest instruction. So if we roll back to this point, what we expect to happen is that all the code we recorded for all the code that we recorded for the lookup will just disappear. So that's something to have up our sleeve. And now what we're going to do is we're going to hop over all of this code that handles all the complicated special cases like calling out the metatables and everything, and we're going to just look for really close to the end. Okay, this is the last bit for loads, and stores are down here. We're only interested in loads for the moment. I'm not sure if we're ever going to really need to deal with stores, because if you store into a sealed table, that's going to break the seal, and that's going to basically just invalidate all the machine code. So it's not something that actually needs to be compiled as I have it in my head right now. So we're only concerned with loads, which is this bit of code here. So ordinarily, this is where we end up. We generate all of our code for lookups, and then we say, return res, which let's double check. It's a typed reference. Anyway, so what we want to do is just insert something very clever here. This is where we do something very clever to support sealed tables. All we need to do a first approximation is to fill in this blank here and say that if we want this sealed tables semantics, then we do something here. So now I think we're just going to kind of reproduce what I did the first time, which is just to hack the VM so that every lookup is treated as being sealed, and then we'll make that work on a trivial example. And then the next step would be to actually introduce a flag on tables to say whether the table should be sealed or not, so that we don't do this. Globally. We only do it where we want it. So first step will be to just do this globally. So now we want to do a rollback, like there's a little rollback there. We want to do something similar to that, where we just nuke all of the code that we've generated so far. So we will say ljir rollback our JIT state to this rollback start position that we remembered when we came in. So anything could have happened here. We might have recorded an array lookup, we might have recorded a hash table lookup with a constant key or with a variable key. We might have generated a tremendous amount of code going through metatables and all kinds of doing arbitrary amount of stuff, and here that all just disappears. So now we don't have any code, but what we do have is we do have some of the information that was generated while the code, some of the information that was produced while we generated that code, and specifically if we open a file called ljrecord.h, there is this record index structure. So this is something that kind of gets filled in while this process of generating a table lookup goes on. So what I hope is that now that we have this information, what was the runtime value of the key, what was the runtime value of the stored object. Once we have this, we should be able to then generate the code that we want based on this this data, which came about as a side effect of actually executing the lookup. So I'm going to try to think this through, and then we can compare it with the code that I wrote yesterday. So we really want to do three things here. The most important thing is we want to put a constant in as the final value, and then the other things we want to do is insert a couple of safety checks. But let's do the fun part first. So here, what we actually want to return, let's say, let's just we're gonna do something better than always true. We're gonna only do this on tables that are sealed. But anyway, we'll delimit our hack that way anyway. We're gonna say that the result should actually be a constant. So I think we have a constify. Yes, LJ record constify. So what this does is it takes a value that we want to make into a constant, and it converts that into an IR reference, a typed IR reference. So what that means is if we have any object that we want to reference as a constant in a trace, we can pass it in here, and it will get kind of interned in the constant pool of this machine code so that we can reference it. So what we want to do now is we want to take the value. We're going to take the value that we got out of our table lookup, which I believe actually is this old v. So that variable contains, I think, the value that came from our table lookup. So this is the thing that we want to turn into a constant. Let's just do that. So we call that constify, LJ, is it just constify? LJ record constify, give it our JIT state, and give it old v. So this is the final thing that comes out of the compilation, and it's going to be a reference into the constant pool of this machine code, and we're interning in the constant pool this value. So so that can be any object of any kind. It could be a FFI, C struct, it could be a table, it could be a function, it could be kind of anything. And by interning it in the constant pool, we're making a reference to it that is visible to the garbage collector and everything. So this will be there. This is an object that now is referenced directly in machine code, and there's nothing wrong with that. There's nothing strange about that. It's something that happens all the time in this compiler. So cool. Maybe we could even try to run this. We don't have any safety checks, but we're lacking so many safety checks that maybe it doesn't even matter when we're thinking about the simple example. Let's see if this compiles, and if so, whether it runs that example program, and if so, what code we get out at the end. What are the odds? Okay, so it compiled. Again, just for context, let's look at the code that we got with the pristine LuaJIT v2.1 on our little example program. There we got all of this code with all of the hash table lookups and the floating point math and the multiplications. Now, will it be a segfault or will it be something else? We run our hacked version. Okay, okay, so this did the right thing, it looks like. So now what we got is all of those hash table lookups and floating point arithmetic and multiplication and everything compiled into just one line of code, which is what we saw before. It all just became the constant 10,000 because once we did all of those lookups and everything, the value that we got at the end, well, a couple of things happened here. Constant folding kicked in later. So hang on, if we would disable constant folding, we just turn the optimization way down. Yeah, right. So if we're just going to see effect of our sealed tables optimization all in isolation. I turn off all of the other optimizations in the compiler, and then what we see here is we don't have any of those hash table lookups. So again, if we just briefly pop back up, in the original code we had all of these hash table lookups for all the globals. Now that has all disappeared here. We don't have the hash table lookups, but we still do have a square root operation, and we still do have a raised to the power of 2 operation, and we still do have a multiplication. So so pulling up our example again briefly, we optimize the table lookup. T.x just became the value and T.y became the value, but we still have this squared here, and we still have this square root. And then the thing is that the sealed table optimization, it interacts so nicely with these other optimizations that the JIT already does, because when we put a constant into the generated code, the JIT is really good at propagating constants around and saying, well, if I know that T.x is 10,000 and I'm going to take the square root of it, then I know that that's 100. So that's what happens then when we run this again with more optimizations, just disabling the loop optimization. Then that just happens. So the existing optimizations in the JIT make all of that arithmetic and math disappear and just become a constant. So this is really, really cool. This is the kind of the promise in some sense of the sealed tables optimization, that if we just figure out large amounts of we just figure out a whole lot of tables in our programs that have very predictable but important values. For example, all of our standard modules, we're not changing the definitions of standard modules very often, and all of our perhaps even application configuration data. If we have a server application that's being reconfigured once a day or once a month or something like that, we might actually quite like to take all of the configuration data and inline that as constants into the machine code and optimize on it very aggressively, just at the expense of having to regenerate the code when the config changes. We, as application programmers, we will be able to make those decisions, which should be really cool, actually, I think. Anyway, that's the dream. Back to the hard slog. So the thing that is totally lacking here is any kind of safety. So this machine code, it's not even really looking at any of the tables anymore. So it's just going to always put this 10,000 in, but it could be that we run this loop once and then we go off and we redefine math.square root, or we replace t with another table or something. So the question is, what should we do there? And what I'm saying with the sealed tables thing is, if we're going to treat the globals as sealed, then when we do the lookup, we want to at least make sure it's the global table that we're looking up. So when we look up a value in a table that is sealed, we want to specialize the machine code for that value in that table, and then take the result and make it a constant. So we've already made the result a constant. Now what we need to do is we need to declare that this machine code is specialized in that way. And the way that we do that is with so-called guarded assertions, where before we use this magic constant 10,000, we say, well, hang on a minute, was it the globals table that we were looking at, and was it the key square root? So we just do the basic sanity check. So we still skip over nearly everything, all the actual hash table lookups and everything, but we just need to make sure that we're still talking about the same thing. And this is so that we don't accidentally make a lookup for one key, the code that looks up one key be reused for a different key, or a lookup in one table be reused for another table. We always want to have machine code specialized for each key and table combination. So if there are 100 different combinations of tables and keys, we don't want to run the same code for all of them, because then we're going to pretend that they all have the same result and crazy things are going to happen. What we want to do is generate machine code for each case as it is. And this may not be the best strategy, but it's the one we're going to run with for now. So we need to generate 2 guards in this code. Sorry, and this was the Emacs we were in. So here there we inline the lookup result as a constant, and we want to also guard that we are looking in the right table, and we want to guard that we are looking at the right key. And again, if the key is a constant, this guard is probably going to disappear because of existing optimizations in the compiler, right? So if we want to guard that the key is square root, and it's being called with a literal string, a literal square root, then the guard can be evaluated at recording time here, and it can disappear and doesn't need to be checked at runtime. So these guards should only actually execute at runtime if there is any uncertainty, which should be actually pretty rare, at least in simple usages like what we have, where we're referring to things by name. So which one are we going to do first? Let's do the table first. We want to emit a guard that the table at runtime will be the same as the table at recording time. So how do we emit a guard? Here is an example of emitting a guard. We say emit an IR instruction. It's going to be a guard. The guard is also going to be equal, and the type is going to be also a pointer to a garbage collected object. No, sorry, it's not, is it? Because the table is its own type. There should be a IR type table, yes. So we're gonna check for equality between two tables as a prerequisite for executing our optimized machine code. The first table is going to be the two tables. One is the actual table we had at recording time, which should be somewhere in this structure. Runtime value of the table or index object. So I think this is the table that it really was when we did the recording. So this is the table that the code is specialized for. So that's one of our operands. And the other one is the runtime table, which I guess is this. The reference. We will try that and see if it gives us what we want. So again, we're very satisfied if we just learn something from all of this. So this code's not going into production today. So we'll take some baby steps and come back and check our assumptions. We'll iterate a little bit. Okay, so we're going to check that the actual computed value of the table at recording time is the same as the value, the runtime value that is the runtime value of the table. So this is the recording time value of the table, and this is the runtime value of the table, I think. And we're going to assert that those are the same. And let us see if that, well, we'll do the same thing. First, let's see if that just compiles. No. Aggregate value used where an integer was expected on init IR. What does that mean? Init IR, we did an equality guard on a table. I think, well, I'm not sure if it's the specific error, but I think what I'm doing here is naughty. I mean, this is a value that we want to reference, but in order, but the guard is not gonna. The guard needs to have an operand, which is some IR, something in the IR. So actually, we need to intern that as a constant, like we did down here. So in the constant pool of this machine code, we're going to have a reference to the table that it is specialized on, and here we're going to use that reference rather than the value, because that's just illegal. So what we'll do here is we'll just constify that right there, and that might be better. So this one, this IX tab, this is already a typed reference, which is an appropriate argument for a guard in the IR. It wants to reference, I mean, we're going to get a guard IR instruction that's going to reference two other IR instructions, which are trefs. So one of the things we want to reference was already an IR. The other one was actually a value of a kind of an object on the heap. So that one had to be converted by interning it in the constant pool. So now it's absolutely going to work. There's nothing that could possibly prevent this from compiling this time. Except that. Incompatible type for argument 2 of record constify. So it didn't like getting a t value for record constify. So what does LJ record constify wants? It wants a t value pointer. Is that all there is to it? CT value, I think that's just typed as a const t value, so it's not actually a different type. It's just a const declaration for that function. Is it as simple as that? It wants it by address. Yes. Okay. So what code do we get now? So in a perfect world, we're going to get the same code now with one additional guard to check that the table is what it should be. Let's see if that happens. Running our new version. So there is our our super hyper specialized machine instruction. So is this new or was that already there? We are. What is this? We do have. We'll see what this line is, and then we'll see if we actually emitted it or not. We do have an equality check on a table, and we are comparing 003. So this, it's a bit of an art to interpret these, but I think that's a reference to the global variable table. So we're checking, is the runtime value of the global variable table, hash table, address in memory, is that the address in memory of the hash table? So what this is, so this must be our code. This is saying, has the global variable table been replaced? Does it have a new address? Is it a new object? In this runtime system, objects have stable addresses in the heap. The garbage collector doesn't move things around. So when you allocate an object, it gets an address, and that address is the same for the lifetime of the object. So what this guard is going to do is it's going to say that if we completely replaced the global variable table, like reassigned _g to be some other table, then this guard would fail and this machine code would not execute, would go and find some other code. So what it means is this code is running in the knowledge that the globals table has the same identity that it had when we generated this code. And that's actually all we need on the table side, because if the table is sealed, and in this case it is because we've implicitly sealed every table in the entire system. I'm going to have to pair that back a bit later. But if the table is sealed, then it's enough to know that it's the same table. We don't need to know anything else. We don't need to check the table is the same size or anything, because if any of those things had changed, it would break the seal on this optimization, which would erase all of this machine code and it would be regenerated. So it's not, the invariant is that any machine code that exists at any given time was compiled after the last time a modification was made to a sealed table. Therefore, in the machine code, you always know that the sealed tables have exactly the same structure and contents that they did when the code was generated, which is very nice. So we are like 2/3 of the way through this quick hack implementation now, because we got our hyper optimized machine code for providing the value. We got our test now that the table is the same one that we generated the specialized machine code for. The only thing we need to do now is also check the value. We need to make sure that that the value we're looking up in that table is also the same one that we generated this hyper specialized machine code for. So if we looked up square root before and now we're looking at sine or cosine or something, then it would be very unfortunate if we used this machine code and said that the answer was 10,000. So we need to check that as well. So let's just do that. I hope it's similarly easy. Sorry, other Emacs. What do you reckon? One line of code. Let's see. We are going to emit some IR. It's going to be a guard again. So what's the type going to be? It's not a table now, right? This can be any object, but it's interesting. So the IR doesn't really have an any object type. I don't think it does anyway. So the IR, this is a very interesting thing about the intermediate representation. So Lua is a dynamically typed language. Any variable can be assigned to a value of any type. It's late bound, anything goes. this intermediate representation used by the compiler is statically typed, so every single value has a very specific type. And when I say specific, I mean like really specific. You don't say something is a Boolean, you say something is either true or it's false. So the IR code is really, really, really specialized very, very aggressively on the value, on specific, kind of types and values. So we can't just say, well, we don't care what the type is here, even though we don't care. We need to figure out what is the type of the key in this specific code that we're generating, and reference that. So we're going to do an equality check. So we are just going to check that the key is the same, and the type we must have calculated somewhere while we were doing the lookup. So something here must be, something somewhere must be the type. Runtime value of the table of the key, stored value, previously stored value, key reference. Okay, so there's no type there. So somewhere, let's say somewhere in as a local variable or something, we must have the type. It only stands to reason. Okay, so this T looks kind of promising, right? Okay, so since we're going quick and dirty, I think that this variable T contains the type of our. Oh, hang on, that's being a bit risky, right? Is that the type of the key, or is that the type of the value? So let's have a little bit of a read and try and see what is the type of our key. None of those is a type particularly. Sorry, I'm being silly. These references are typed. So we have a reference to the key. A tref is a typed reference. Unless I'm going totally off the rails, it's a typed reference into the IR. So it's actually two things. If we look at a tref, it's the index into the IR, and it's also the type. So a tref is this. So we should be able to look at the reference to our key and strip off the type from that and reuse it. So how do we do that? There are surely some macros for manipulating trefs. They're probably in ljit.h. Probably called tref underscore something. No, they're not. Let's see if there's somewhere else that we are. I typed. Okay, so this is where we take we could do it this way. This is where we take an actual value and convert and pull the type off that and make it into an IR, intermediate representation type. That would actually be fine, although it seems a little bit indirect. If we already have a typed reference, we should be able to pull the type off the typed reference. IR type underscore. Is that the macro that we want? IR type. No, it's not. Is that the one we want? IRT underscore. That looks like what we want. Let's check for usage of that. IRT type. That's so obscure that it's not used. What do we want? Where is tref defined? Tref is in int32. You construct a tref by taking a ref and a type and moving the type into the high 8 bits. So we're looking for something that shifts those back, which certainly looks to this. Tref underscore t. Aha, well that sounds kind of like what we want, right? Tref t. Tref type might be a better one. So that's something here, tref type. Is this something that is really used? Yes. Okay. I think that's what we want. So when we put in a type, we're going to say tref type, and it's going to be we want the type of the key, so, and here's the tref to the key. So we're going to hope that we can say tref type of this record index structures key field. That may possibly work. Okay, so we're trying to emit an equality guard for the key that we're looking up in the table. So far we're emitting an equality guard with the type, same type as the key, which might be an integer or a floating point or a string or whatever. And now we need to provide the operands. So we want to, as before, we wanted to, we need to take this value that we specialized on, we need to intern that in the constant pool. Which should be something like that, right? That's the value of the key. And then we want to compare that with the runtime value of the key. Can it be that simple? We emit something in the IR, which is a typed guard. I assume that means the guard is checking equality. The type is the type of the key that we looked up in the table when we generated this code. We want to check that we want to assert that the value is one of our operands to the equality is the value of the key at the time we generated this machine code, and the other is the runtime value of the key when we're running it. So what this does, we hope, is it asserts that the runtime value of the key is the same as the value that we specialize the machine code on. So then we should have the code that we want, right? We when we run this, we say, is it the right table? Is it the right key? If so, just use the constant that we already inlined into the machine code. And we might have to be a bit careful to actually see this, because if we're looking up, if we have a lookup like, again, let's look at our program. If we do a lookup like math.square root, so square root, that's a constant literal, so the compiler is probably going to actually optimize away that guard a lot of the time in simple uses. So if what we're looking up is the string square root, then in the IR this is going to say if the constant square root is equal to the constant square root, and it's just going to disappear. So maybe we'll need to either make some creative examples or disable a lot of optimizations to actually see this guard. Let's see. But first let's see if it compiles, and then let's see if it crashes. So it compiles. First time, which is of course very ominous. And what happens when we run it on that same example? So I think we got exactly the same code as last time, right? We have one guard, which is checking equality on a table, checking that the global table hasn't been replaced, which would invalidate our machine code, and then it goes down and does this heavily optimized code. So if we disable all other optimizations, then can we see our guard? Yeah. Ah, cool. Now we see a bunch of these. Every time we do a table lookup now, we see a pair of guards. We want to look up math in the global table. First, we make sure the global table is still the global table. Then we make sure that the runtime key is the same as the compile time key. In this case, they're both constants. Is the constant math equal to the constant math? So it's clear that this should disappear in compilation if any non-trivial optimizations are running. So the only reason we can see this code is that we disabled all optimizations, apart from sealed tables, because we just put that in very directly. We're going to need to conditionalize that like the other optimizations later. So that's really cool. So now we see what an unoptimized sealed table lookup looks like. So for each of these, for the math table, the square root function, t.x, t.y, all of those things, we have just, instead of actually doing a hash table lookup, there's still no hash table lookups here, right? Not a hash table lookup anywhere to be seen. All we do is we make sure that the key and the table are the same at runtime as they were at compile time, and in that case, we know that the lookup that we did at compile time is valid, and we don't need to actually perform a runtime lookup. And if these equality assertions fail, then that just means that we bail out to a side trace. That means that this is not the right machine code. We need other machine code, or we need to back out to the interpreter or whatever, and that's fine. That just means that as soon as it fails, it's not an error. It's not anything like a runtime error or anything like that. It's just a branch out of this machine code, which is specialized for the wrong case, and then to chain off and find something more suitable. So that's fine. So if we compile that again with more optimizations, this looks really good. I mean, that's the code that I want. We've got here a single check that the global table hasn't been replaced, and then we've got this, we're just using a constant, and that's replacing, like, was it 3, 4, 5 hash table lookups and a floating point square root operation and a couple of multiplications and everything. So that looks really, 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 really good. So maybe we'll quit while we're ahead now, because we've been going for a while. And the next thing we're going to want to do is, now we've made this a global thing that applies to every table. So crazy things will probably happen. Maybe it will be fun to actually run this on a standard program just to see what happens, but it's unlikely to give us the semantics that we want. I think what we want to do is be able to declare which tables we want to consider sealed and do this optimization on. So for example, all the standard modules probably in that category, because we're just not redefining functions like math.square root very often. Certainly we want to optimize for the case where they haven't been redefined. And then we want to do some kind of a little API, and we've only tested this on really trivial examples. So we want to test this on things like metatables, which are going to recursively enter this function we've hacked, and are almost certainly going to do something completely wrong with the code as it is written. So we need to do a slightly less trivial testing, but we're going to go in baby steps. And I'm actually kind of looking forward to that. So we'll see how this particular live coding topic competes with other topics that are going on as well. Often I am working on a dozen different problems at any given time, and often I'm stuck on most of them. Like there's an optimization I was thinking of doing, and I went a little way towards it, and I found a fatal flaw, and I need to go back to the drawing board. So that kind of goes to the back of the queue. This one is going surprisingly well so far, so we'll see. We'll see whether that continues, whether we can put it down and do other things, or what we want to do. Anyway, enough streaming for now. Thanks very much for tuning in.